Hi, this is the supplemental video for Homework 2. As you can see, I've already started doing some of the work here. How to make a chart and label it and whatnot was covered last time. What we have here is a graph of the Vostok ice core data, and it's one of the deepest ice cores that has ever been taken from East Antarctica. And this is the CO2 data that was extracted from it. I've organized the years as negative numbers just before 0. So the most recent information from the ice core was 344 BC. So we refer to this as pre-industrial. It's well before humans were doing anything on any sort of massive scale. So it gives us a view over about almost 500,000 years as to what the atmospheric CO2 concentrations were like. Another thing you can notice with this data is it's vast. If you move down the page here, there's lots and lots of data. And we'll do this several times this semester, look at large data sets. The last piece of data here is at 364, and it starts at 2. I'm going to make a note here, 2 to 364. We're going to need that in a moment. Now, one of the things I ask you to do in this homework is to find the minimum CO2 value, the maximum CO2 value, and the range for both the Vostok and the Mauna Loa data. So let me show you how to do that. With spreadsheets, if you enter the equal sign, the spreadsheet thinks you're about to enter a formula. Well, here's one, MIN. It will give me the minimum parenthesis of whatever range of cells I asked for. So let's do B2. You can see B2 is highlighted, colon B364 parenthesis. This tells the spreadsheet I want the minimum number out of all the numbers between B2 all the way down to the end. I hit enter. So that would give me the min CO2. It's in ppm. If I want the maximum, it's MAX, maximum value, parenthesis, B2, colon B364, parentheses, gives me the maximum value. And then if I want the range, all I have to do is I can click one of these cells, that's E3, minus, click the other one, E2, hit enter, and it does the subtraction for me. So this is part of the utility of a spreadsheet, is you can do a lot of calculations directly in the spreadsheet. So I ask you to do this for the Mauna Loa data as well, and then to compare the range, how much is fluctuating. Now when you look at this graph, it looks like things are going down and up and down and up and down and up quite quickly. Usually folks look at this and they describe the levels as being sporadic or volatile or whatnot. Well, I want to examine this claim. I do ask you to talk about it in the homework. Certainly it is affected by how the graph is portrayed. Things look less rapid now than they do if you scrunch it all together. Consider that in your answer. The other difficult thing to judge here is this a steep change? We're looking at about 500,000 years. So what we're going to do is we're going to look at a lot of slopes. We're going to imagine that if we had connected all these points together and we looked at all the different slopes of those line segments, we can get a sense for how things were changing from one chunk of time to another. Now these are not these aren't uniform. Here's a 1,300-year difference. Here's like a 300-year difference. Here's like a 2,000 or 3,000 year difference. So the differences between these pieces of data isn't uniform. And that's fine. We're just getting sort of a sense. So if I do equals again, up here in C2, I'm going to do parentheses. I want to do the concentration, B2, minus a previous concentration, B3. Put those in parentheses, divide, parentheses, and then the corresponding times, close parentheses. This is just your y2 minus y1 over x2 minus x1. You hit enter, and it computes the slope for these two. Now, if I select that cell, there's a little square here. And if you put the little crosshairs on it and double-click, it'll fill the entire column with that formula. So that's kind of handy. So there's lots of different numbers here, and lots of them are small. Take a gander here. These are all 0.00, 0.00, 0.00. Overwhelmingly, these are small. So what would happen if we looked for the min slope and the max slope? Easy to do. Equal sign, min, parentheses, C2, colon, 3, as our C. We'll do 363 because we don't actually care about the last cell. Oops. Yeah, we'll talk about that in a second. So actually, let's scroll down through here. There's one funny number here. There's a division by 0, and I'll tell you why that is, or why it's likely anyway. Right there. So why is there division by 0? Let's delete that. You'll notice that these 2 years, 407,000 BC and 407,000 BC, are the same year. I've talked to a climatologist on campus about some of these data points. He says very likely these were just measurements made very close together. There is certainly uncertainty in the dating. So this is 407,024 years BC, plus or minus a couple. So not to worry too much about that. There's some redundant data points in here that are actually going to affect us in a couple other ways. I'll show you in a minute. Page up. So now that's better. And now let's do max, M-A-X, parentheses, C2 to C363, parentheses, enter. Now, we get these two numbers. This should be a little suspicious because most of the numbers we saw here are 0.0 something. So what's going on? There are a couple outliers here. Let me show you where these are. Right, and suppose, actually, before I do that, let me make another chart. So suppose I did, let's do, so this is rate of change, C. If I highlight B and C, and then I insert a chart, and here we go. So here's a scatter plot, and here's what's being plotted. The vertical axis is the rate of change. It's the slope that we're talking about, ppm per year. And then, oh, actually, this isn't quite what I wanted. Select A, and then Control C. So, and then do insert chart. And so this is the rate of change versus the year. So what we see here is there's a couple outliers. There's the 1.9 that we found. That's our max, the largest positive number. Here's the min, negative 1.75. So, and they're quite close together. And then every other rate of change, there's a couple little outliers here, 0.22. But every other rate of change is 0.00, 0.00, 0.00, 0.00. So they're all pretty close together. So what's happening here? Right around 217,000 BC. I do ask you to make a graph like this. So if we go down and look at those, this is another question I sent to my climatologist friend, and I'll tell you why in a moment. So where was it? 207. There it is. So what's happening here is if you double click on this, it's comparing these cells. These two dates are a year apart. But again, there's an uncertainty in the dating of the air and the air bubbles in the ice core. So his thoughts are these were just repeated measurements to gain more data. He wouldn't put a lot of faith in these being actually 1 year apart. So it's a little bit like the divide 0 kind of thing. So this is not likely to be significant. So, and here's the other one, right here. Here's a very large negative change, and again, it's potentially a 2-year difference. But again, the uncertainty in these dates is within a couple of years anyway, so these aren't to be relied on too much. So what does that mean? Well, it means that if we're going to think about trying to compare the actual rate of changes that we're witnessing here, these are two outliers, clearly the oddballs out from all the other rates of change. So we've got a couple options. One is to compute an average. So we do an average rate of change equals average, and I can take C2 to C363 parentheses. This is the average rate of change. So it's pretty small. Now there's a problem in this too, in that while we're averaging negative and positive numbers together, what happens? Well, if you take plus 1 and then you add negative 1 to it, you're going to get 0. So an even better way of doing this is to do equals ABS, that's absolute value of that number. Hit enter. And then double click that little box again. And you see it just takes the absolute value of every one of these numbers. So now here's a better way of doing it. I just want to cross that out. So let's do an average rate of change, absolute value. So now I can do average D2 to D363. This is probably a little bit better. So this is sort of a real average rate of change. So you can use, I would use this number. I ask you to compare this against the average rate of change for the Mauna Loa data. The Mauna Loa data also has some little drops and whatnot. But so these things are also going to do for the Mauna Loa data. And I also want you to do a graph of the Mauna Loa data of the rate of change versus the year, again, to compare them. Now, with the Mauna Loa data, I also ask you to compare them in terms of ratios. So you're going to take the Mauna Loa data, the Mauna Loa average, and divide by this average, which is going to give you a number which will indicate how much more the average rate of change of present CO2 concentrations are versus the pre-industrial. And it's several hundred times. So it's not just that current levels of CO2 are higher, it's that the rate of change is several hundred times faster. And this we're just extracting from the data itself. All right, so be certain to actually read the homework assignment on Blackboard. Make sure you're completing all the things that are asked. You're going to have a bunch of graphs, a bunch of calculations here, a bunch of comparisons. And don't forget to think about this graph here. Again, it looks like things are really going up and down rapidly, especially when you compare it to your Mauna Loa CO2 concentration graph over the past 50 some odd years. But consider the slopes in this graph versus the slope of your linear model in the last homework, and kind of reflect on that. And these graphs are very easy to misinterpret, certainly. Okay, good luck.